So this is Ansys environment. Now, as we discuss steps in any CAE software, okay, or CAE process, are three different phases are there. So pre-processor, solution, and post-processor. Okay. So here we see the pre-processor, solution, general post-processor, and time history post-processor. So this is time-dependent analysis. Okay, and general post-processor will give you the results. Okay. Now today we will see how to perform simple analysis in this environment. So we will learn say preprocessor, solution, and general post processor. There are many things are there. Out of that, today we will just see the how to solve a simple problem. Okay, so that we will be conversant with the environment. Okay, now in preprocessor we define the problem. Okay, so today we will consider that okay our model is of a say a different shape. So it will not be able to model it as a 2D model or a 1D model. Okay, so we will model the things as a say solid model in a Creo software and then bring that model into Ansys environment. Change job name. Okay, so we know the Creo. Okay, so we start with new part. Say A. Okay, here we will select the unit system. So when we bring this component into a Ansys environment, so all this unit system will also come to with that. Okay, so Newton seconds. Now we will have one spanner and we will perform the analysis on the spanner. Okay, so start with extrude. Okay, we'll model the spanner. Uh, Simple model. Will not go much in details. Okay, close. Let it be 62. Okay, then we will align this center on this axis, center on this axis. Okay, then okay. Now let's have one axis here, okay, for the symmetry purpose, so that whenever we draw a particular line, let it complete here only. Okay, now this line we will mirror about this. Okay, now 400, 60, and let it be 60. Okay, then what we'll do is okay, then we will remove the lines which are not required. Okay, say 30. Okay. A thickness, let it be 15 mm. Okay. Now this is a sharp edge. Okay, we will keep it as a sharp edge, and next phase we will modify that. Okay, so just save it. Okay, so okay, now we will save it as a IGS for the export purpose. Save a copy, and done. File type is IGS. Okay, so new file name, say A. So we define A1. Okay, so we created a model. Okay, we convert that model into a neutral database, and then we will now bring this model, solid model, in a Ansys environment. Okay, so before that we'll see preference. Now in Ansys we can perform different types of analysis. Okay, now out of that we want to perform the structural analysis. Okay, we want to apply the forces and want to see the stresses and deflection. Okay, so that is called as a structural analysis. Okay, so we will select this structural analysis so that the whatever the database available for the elements and different properties will be restricted. Okay, this H method we will discuss afterwards. Okay, now here we define the preprocessor. Okay, from here actual work of a say CA software or FEM software, FEA software starts. Okay, now we will select, this is a 3D model, whatever model we have created. So element type required will be a 3D element. Okay, so we'll add the element, add. Okay, these are the different types of elements which are available. Okay, now out of this we will select a solid type of element. Okay, this can be a 4 node 182, that is simple plain element, that is 2D element. 8 node 183, again it is a plain element, 2D element, and brick shape element is a 3D element. So we will select 8 node. 20 node is higher order element. We will now select that. Okay, brick 8 node 185. Okay, so this element is selected, close it. Okay, done. Material properties, material models, structural, linear, elastic, isotropic material. Modulus of elasticity of steel is 2.1 E5 Newton per mm square and 0.3. Okay. Okay. We have defined the material property.
Excuse me, sir.
Yes.
Sir, what was that 2 point you put? What was that value, sir?
Modulus of elasticity. E.
Modulus of elasticity. Okay, okay.
Okay. Material properties required are modulus of elasticity and Poisson's ratio for simple structural analysis. Okay.
Okay, sir.
Now, if you want to perform dynamic analysis, in that case, weight matters. So in that case, we have to put the density. So it depends upon the analysis to analysis whether we want to consider the self weight or not. Okay, then modeling. So what we want, we are not going to create a model here because it is very primitive type of modeling facilities are available in the Ansys, because this software is not for the, say, for the modeling purpose. Okay, so what we will do, we will import geometry. So import IGS. Okay. Say A1 IGS. Okay. Okay. So whatever the geometry we have defined, okay. So here is a geometry. Okay. So these are the views, isometric view. Okay. So now what we will do, next step is to, this is a geometric model. Now we want to convert this geometric model into a FEA model. Okay. So geometric model consists of say points, lines, surface, and then solid. Okay. Where FEA model consists of nodes and elements. So we will mesh it, or we call it as a discretization or a meshing process. So we will go for the meshing. Whatever the element we have selected, we'll divide this solid model with that particular elements. So smart size, it is automatic meshing, say fine to coarse. Okay. So we'll select the parameter as a 4, mesh. Close. Okay. So meshing is done. Now these are the elements and the nodes. Okay. There is no undo command. So whatever the commands we are giving, so be careful while defining commands. We will not see any undo command here. Okay. Now we will, this is a FEA model. Now we want to apply the loads and the boundary conditions. So loads, define loads, apply structural. Okay. So displacement of this, where which is engaged with the either nut or bolt, will be fixed, and we will apply a force in this direction, downward direction here, in the y direction. Okay. So displacement on area, on this area, and on this area, the displacement will be on all the three direction will be 0. So no need to write down the 0. By default, in case of Ansys software or any FEA software, if you are not putting any value, it understands it is 0. Okay. So it applies the boundary condition that this will be fixed. And now we will apply the forces. Force on node, say on this 4 node, we will apply the, okay, in y direction, downward direction defined by negative, say 500 Newton on each node. So total 2 kilonewton force is applied. Okay, close. Okay, now it consists of nodes, elements, fixing condition, and the load. So this much is required to solve any problem. Okay, so sufficient data is there to solve this problem. Now we want to see the deflection. When we apply this force, what will be the deflection and what will be the stress distribution. Okay. Solution, solve current LS. Okay. Solution is done. Close. General processor to see the results. So we will see colorful plots. Plot contour plot, nodal solution. These are the different solutions which we can see. Okay, but we should know that what exact solution we want to see. The degree of freedom solution means displacement. So displacement vector sum. Okay, so now we can see the deflection 2.555. So that will this will as this is fixed, this is going to be like this only. Okay, now this is the deflection at each and every point. Okay, now this color range defines the deflection range. Next is we want to see also the stresses. Stress, these are the different types of stresses which we can see. Okay, out of this we will see the one measure stresses which are derived from the three principal stresses. Maximum stress value is at this location and it is 237. Okay, now we know that okay uh, this stress is because of the stress concentration. Okay, whatever the value is there, and this is sudden change in the or this is a corner. Generally we do not have such thing in a design. Okay, so this is because of that. So what modification we can do, what we can have a fillet here. Okay, so just plot control hard copy to file. Okay, so jpeg. Okay, so it will save this. Okay, so it will be useful for the comparison. Okay, so now what we will do, we will perform another analysis where we are going to modify our model, bring a current model here and do the analysis. So for that purpose, what we will do, instead of starting again, okay, so, okay, let's start again because otherwise we have to delete 111. That purpose we have to delete the loading condition, then uh, nodes and element, then solid model and so on. So instead of that, save this as file, clear, start new. Okay, yes, file, change job name A02. Okay, so let's first we will modify the model here. Now what will round? Okay, so here a 20, 20. Okay, we have modified these things. Okay, instead of sharp corner, we modify this. Save it. Again, file, save as, save a copy, IGS. So it was A1. Now we will save it as a A2. Okay. Okay. So next, again, the Ansys environment, preference, structural, okay, preprocessor, element type, add, edit, delete, okay, solid, brick element, okay, close. Okay, material properties, material models, structural, linear, elastic, isotropic, modulus of elasticity 2.1, E5 and Poisson ratio 0.3. Okay, clear. Next is file, import IGS, okay, browse A2, open, okay. Okay, so now this is new model. Now meshing, mesh tool, smart size 4, parameter 4, this one, okay, close. Okay, so no more number of nodes and elements are here. Okay, what is next phase is we apply the loads and the boundary condition. Save database, loads, displacement on area, on this area and on this area. Okay, what fix? Okay. Okay. Next is structural force on node 1, 2, 3, 4. Okay. Fy minus 500. Okay. Close. Okay. Everything is we have defined. The solution solve current ls. Okay. Yes. Close. Okay. Now we get to general post processor, plot results, nodal solution, one message stresses. Okay. Now can see that though the value is more, the results are correct because we have the fine smooth portion and then there is no drastic change in the cross section. Okay. Okay. So what we have modified? We have modified the design. Okay. And we know that just by simply modifying these things, okay, so we get the results very fast. Okay. Now what we will do is now we will see the deflection, nodal solution, displacement vectors. Okay. So 2.831. Okay. Now if I want to change the material instead of still if I manufacture this spanner with the help of say aluminum, okay, preprocessor, material properties, material library, oh, sorry, material models. Here we have defined the material. Now instead of this, what we will do, we will have a aluminum 0.7 E5. Poisson's ratio is okay, 0.29. Okay. So we have changed the material. Now once we change the material, save it, solution, solve, current ls. Okay. Yes, solution is done. Post processor, plot results, nodal solution, displacement vector sum 2.831. Now the deflection is 8.55. So once we create a model, now once if we want to change the material, okay, this will be the change of the material, effect of the change of displacement will be more. The stresses or the stresses depends upon the stress value is a same. Okay. So if you change the material property, deflection will be different.